So, good morning, everyone. My name is Steve Eisenreich. I have had the pleasure for the last 15 years at least of working on what I consider and what many consider really landmark pieces of water and environmental protection legislation in Europe. The first one, of course, the Water Framework Directive. Mr. Pesce has already given you some frame on that. I'm going to go over that in a different sort of way. And also I had the pleasure of leading the Joint Research Center of the Commission effort in the implementation of REACH, so the scientific implementation of REACH activities, which is all very interesting. I was given the task to talk about the scientific challenges embedded in the various types of water legislation over the last 15 years, which is one hell of a task, I must say. So I've had to narrow it down quite well. I'm going to address both Water Framework Directive and REACH and what I consider to have been the most significant challenges, some of the successes, and of course some of the things that are not yet done or not yet done very well. And two messages that I want to leave with you is the generation of fantastic quantities of data that are being put together in various forms on water bodies in Europe or on, let's say, properties of chemicals, etc. And this data is being collected, stored, and integrated in such a way like never before, that it can be used for all of the purposes that you can imagine. Of course, having data isn't enough. It's information. It may even be knowledge, but it doesn't lead us directly to the assessment of the impact of that particular one. Now, you Italians recognize this very well. I say this because I was headquartered at the JRC in Ispra, Italy, on Lago Maggiore for several years, leading the implementation of the Water Framework Directive on the science side for the Commission, and then later the European Chemicals Bureau leading REACH implementation. And it was a tremendous experience to do this because the JRC is the place that provides, or should provide, I should say, the scientific basis for good policy making, working directly with the policy relevant Directorate Generals in Brussels, DG Environment or DG Senko, etc., and then with the member states. Just a quick reminder on the Water Framework Directive. You have already seen this and already know it very well. There have been some major and even in some cases extraordinary successes of the Water Framework Directive. What you must understand too, it is the first water protection regulation worldwide that actually is framed around ecological functioning of water bodies. This creates an incredible number of serious scientific questions. So in November of 2000, if you first read the various articles of the Water Framework Directive and you were involved in some way of having to implement this across the European scale, you have to ask yourself, how am I going to do this? How am I going to do that? Science had not really accelerated that way. And so one of the things that the Water Framework Directive did is accelerate the development of very high quality, robust science. And in fact, it has taken a leading global role in other countries looking at how to view water bodies because they view them differently. One of the major successes, of course, was in fact mentioned earlier, was the creation of the adoption, let's say, of the river basin management planning process and the major public participation, the separation of Europe into 130 river basin or river basin districts, the international character. And this process has been very, very successful. There have now been almost full compliance with preparation of these 130 river basin management plans by the member states and the authorities. Not all of them. There's still a long way to go, but of course it is a project. One of the other major successes is in fact the way they structure. Now, one doesn't think about science in terms of how you organize the political implementation structure. But they foresaw and created the common implementation strategy, which the lead was provided by the water directors. These are the chief water people in each of the member states. A scientific or strategic coordination group was made up of those plus other members. And then various work groups or packages of clusters of work groups that addressed various problems. This is the form of the CIS organization as it stands now and then for the next year or two. It's separated into water status clusters. That is, these are the working groups made up of member state experts, hundreds of them, that are still trying to finalize all of the details related to determining ecological status, water bodies, biological quality elements, etc. And there's still a lot to do, along with chemicals. There's a water management cluster, and this cluster's job over these next years is to integrate the character of the Water Framework Directive into other EU legislation. The various agricultural things, for example, and floods. And the third one is a group on knowledge integration and dissemination, which is a group that talks about gathering together the data and interpreting the data in terms of economic impacts and economic opportunities, and also to create a framework for using all of the vast quantities of data that are accumulated throughout this process. Now, this diagram, of course, is very simple in describing the ecological quality ratio, but think of the scientific questions involved. You're faced with this. The obligation now is to establish the ecological quality ratio and the ecological quality status of every water body in Europe by 2015. It ain't going to happen. It will not happen. It's a journey, maybe by 2030. But the questions are, now we have to face what do we mean scientifically about ecological functioning of a water body? This is not water quality per se. The water quality frame is built around whether this water body is functioning ecologically. And that means, of course, trying to understand what that means. How do I determine it? How do I implement it? What do I measure? How do I measure it? How do I interpret or model those measures? The ratio is let's call it a concentration in the numerator about biological quality elements. What biological measurements in water can we make that can assess the ecological quality of the water? Well, they've decided on phytoplankton, macrophytes, benthic invertebrates, fish. But of course, this also has to be determined for every water body in comparison to a reference value. What might this water body have been like 100 years ago or when it was in pristine conditions? How do you actually determine that for these biological quality elements? So there's a lot of effort gone in to trying to understand the science and implementation of these factors. And they've been very successful. And one of the mechanisms by it happened was the rather generous funding in the various European Commission framework programs, FP5, 6, and 7, on water projects. Now, I borrowed this data from my colleague Panagiotis Balavanis in DGRTD in the Environment Directorate. This is the one that funds the major research in the framework programs. And it points out that in FP5, 6, and 7, if you put together the data, there's been more than 600 million euros in European scale research funding given to projects addressing directly or in some cases indirectly the Water Framework Directive. In addition to that, you can see in FP6 and FP7 there has been something like 1.4 billion euros which have been given over to water studies, dedicated to water studies. We know the member states have invested at least the same amount as European frameworks have in trying to study and implement this. So this has been a big factor in pushing this ahead. Hundreds of projects, thousands of scientists, etc. One of the outcomes of this was, of course, once you had the criteria set, what to measure, was the creation of monitoring sites to monitor on a regular basis, annual or monthly, depending on the parameter, what was in the water, what was in the sediment, what was in the biota, etc. And so as of 2012, there have been more than 12,000 routine monitoring sites scattered as you see here. Don't worry about the parts of Italy, Spain, and Portugal. These are ones where the river basin management plans are not fully adopted, but indeed the monitoring programs are implemented. And so this would mean then a rather unbelievable collection of quantities of data. There are something like 42,000 sites at which biological quality elements are being measured, or let's say stations that are being measured. Hydromorphological, physical, chemical quality elements, the priority substances, priority hazardous substances, and other elements which are typical to that river basin. But in any case, there are tens of thousands of sites, hundreds of thousands of samples, and how many thousands of data are being generated. And the question is, what do you do with these data? Now, I've stolen this just as an overlook from my colleagues at the European Environment Agency. As the river basin management plans and progress toward implementation of the Water Framework Directive have been looked at through 2012. And you can see here, for example, for the rivers and lakes of Europe, you see a percentage of the water bodies which are at present in less than good ecological quality. Remember the overriding criterion driving force for the Water Framework Directive, that every water body in Europe should have good ecological quality status by 2015. Well, we can see, of course, that most, in some areas, nearly all water bodies are at present, after this many years of the Water Framework Directive, not of good ecological quality status based on the measurements that are done. There's still a lot of measurements to be made, and the challenges are there, but it raises, of course, the issue whether or not the objectives themselves have been played out properly. In some areas of Belgium and Netherlands and parts of Germany, the water bodies are so heavily modified and are classified as so heavily modified that they will probably be exempted from having to, and in fact may be impossible to achieve, good ecological status. There's another side, though, than the biological quality elements, and that is what chemical pollutants are in water. So part of the Water Framework Directive has to do with selecting, identifying chemical pollutants under a certain type of criterion process that will have to achieve environmental quality standards. The interesting thing about this, if you read the bottom part, water bodies that have annual average concentrations of priority chemicals on this list greater than the established environmental quality standard through risk assessment are defined automatically as not good quality. That is, no matter whether the water body has achieved good ecological status or not, if one of the chemicals on the priority substance list on an annual average basis has a value, as an average value greater than the environmental quality standard, it is defined as not of good quality. This is extremely important because that boundary between good and moderate status kicks in very important economic measures to change that situation so the water body is. So it's a scientific question of major importance and a huge economic question. Well, what are these chemicals? This is sort of my view of the cosmos of chemical pollutants that I've spent most of my life working on. The Water Framework Directive has gone through 2 revisions of the priority substance list. The first list is in the, well, you can see it. lists 33 chemicals, and the second revision is an additional 12 chemicals with these 3 on the revision list. What you see on the black that are under the initial 33 chemical groups, these are almost overwhelmingly legacy chemicals, PCBs and other chemicals like them, and certain pesticides and paraffins. And these compounds have been used for many years. They've been studied for many years. We have a good understanding for most of them. The risk assessments have been done, and the environmental quality standards are quite robust and agreed not only in Europe but internationally. But for the most part, we have put into place technical or engineering solutions, bans, chemical substitutions that in fact are putting these on the back burner. In the future, I would see many of these coming off the priority substance list because they will no longer be detected at significant values in many of the member states. But the second revision starts a whole new game. These are now chemicals that are largely not legacy chemicals. These are not emerging, but let's say newer chemicals that we've sort of known about for some time, but now we understand more about them in terms of their potential toxicity in the system. We know much about their emissions to the environment, how they behave in residence time, etc. And now these have very few of the legacy characteristics. These are the dominated by the agricultural chemicals, let's say, a few other combustion byproducts like dioxin and dioxin-like PCBs, which probably should have been on the first list. But in any case, we now are moving into areas where new bans, new substitutions, and new policies are and will be put in place to reduce these in the environment. There were 3 compounds in that revision process that were suggested to be placed on the priority substance list and were not agreed to by the European Council and European Parliament for very good reasons. One of them is diclofenac. Diclofenac is a pharmaceutical, the first pharmaceutical, if you like, on the priority substance list, even on the watch list. At the time this was being discussed, there was a lot of opposition to putting it on, not so much because of potential toxicity related to diclofenac, because we didn't know enough of it, and there were not enough measurements in water bodies of the member states to make it a European issue. Well, now there is, and diclofenac is one of those compounds that is put on this watch list for very careful monitoring in the system, but not yet on the priority substance list. The second 2 are, of course, estrogens, endocrine disruptors. One is natural, one is a female hormone. And these occur at remarkably small concentrations, but they are measurable, and especially in terms of their impact, especially in wastewater effluents and receiving waters. And these were not put on that list because indeed there weren't enough detailed measurements, the analytical procedures were not well worked out, and the impact on the aquatic system was not well understood, but people understood enough, as you will understand, most of you, that this is a serious problem. So if you're going to choose priority chemicals, you normally would go through a process. The legacy chemicals have gone through all of these steps and are being banned or substituted and not being used or will not be used much in the future. Some of the compounds on the second revised list have gone through half of that, where now we need to understand more about their occurrence at the European level in all these water bodies and understand more about their risk assessment. But indeed, the pharmaceuticals, the veterinary medicines, and many of the personal care products have not gone through hardly any of this identification process, and it's being looked at very carefully. So these compounds get discharged to the environment. Where do the pharmaceuticals come from? The major source of pharmaceuticals to water bodies is through wastewater treatment effluents. There is a passage through wastewater treatment. In fact, it comes through normal human activities into the toilet, down the waste stream, into the waste treatment system. The waste treatment systems, as they're operated, are not dedicated to the specific removal of these compounds, and most of them are not removed very well. Some of them are metabolized into other endocrine disruptors and relates to a problem. We are now beginning to understand that plant industries also are major emitters of estrogenic compounds, and where these plant industries feed into the wastewater stream, it also comes out in the wastewater treatment system. There's a very interesting paper that just came out. I won't ask you to read it, and it was a, let's call it a first look based on the data available, and the question was, do concentrations of these estrogens and diclofenac, as these three on the watch list, are likely to exceed the environmental quality standards which have been proposed to them, for them. So I just took out this particular phrase, which basically says that the mean concentrations of the EE2 compound, that's the 17-alpha-ethanol estradiol, exceed the projected environmental quality standards, which is very low, 0.035 nanograms per liter, 35 picograms per liter, and approximately 12% of the river lengths across the EU. So this is going to be an issue. However, in some countries, this, particularly in Belgium and the Netherlands, this increases to nearly a third of the river stretches have concentrations which exceed that. So clearly, if one is interested about estrogenic activity, endocrine disruption, effects on the ecosystem, and even the flows into groundwater, etc., this is going to be a problem. Now, one of the ways of dealing with these huge data sets is a new program. It's an initiative started a few years ago. It started slowly of Director General Environment and the European Commission, and also the technical coordinator and builder is the JRC, and it's called IPChem. So it is a single access point, or will be a single access point for locating and retrieving all chemical monitoring data which are managed through the regulatory process or donated to it from research programs of a certain quality. And it basically will support a more coordinated approach to collecting, storing, and particularly assessing data which are being collected, which were not put together at the European scale. It's a very robust database. It's built up of 4 modules: the environmental module, monitoring module, which should include basically all of the monitored chemical and biological information as a result, not only of the Water Framework Directive, but other member state activities as well, including the emerging chemicals that are being mentioned. This is being coordinated by the European Environment Agency. Human biomonitoring, also coordinated by the EEA. Chemical product and indoor chemical air data, which is coordinated in the module by the JRC. And of course, chemical aspects in food and feed through EFSA. The biggest challenge, I mean, building, okay, first of all, IPChem is built. A prototype exists. It's been tested on a few databases of collaborators who have donated data sets, rigorous, quite robust data sets to make it work. The difficulty and the challenge is really populating the database with those data. If you understand that there are 12,000 monitoring sites of water bodies in Europe, priority substances, etc., are being collected, those sites are being monitored for chemicals 12 times a year. So there's a huge, huge, huge quantity of data that's being generated. Now, the member states typically only report data to the Commission for a regulatory purpose where the value exceeds the environmental quality standard. So 95% of the vast, huge database is empty, even though the data are developed. Now, the member states have the data, and so it's convincing the member state authorities to then give the actual data to populate it, and there's a lot of support for doing this. I guess my time is up. I should probably... this is going to be difficult. How much time do I have?
5 minutes.
Okay. Let me say a few words about REACH because it's, of course, it is the gold standard. You probably know now that this not so new anymore EU chemicals legislation has been adopted word for word into the legislation of 20 other countries in the world, including China, Japan, South Korea, Egypt even, and it's been adopted word for word even in Turkey. And so it has become gold standard with respect to chemical, or safe use of chemicals, safe management of chemicals. There are about 100,000 chemicals on the EU market, going back to about 1975. The European Chemicals Agency anticipates that they will receive about 30,000 REACH registrations. All of the chemicals that are on the market at one time or another will have to be re-registered under REACH. Of course, new chemicals will have to be registered. As of a few days ago, in the database there are 12,735 unique substances which have been registered in something like 49,000 registration dossiers. This is a requirement of REACH. Now, REACH is different in the most essential feature is that the responsibility for the safe management of chemicals moves from public authorities to industry. And of course, making that happen has been the biggest challenge of all. Going back to data. I have here at the bottom of the page a need for that all all chemical registrations have to have a rather large extent of data, and if those data are not delivered, that chemical cannot go to market. And so the data that is required by an industry to submit in support of the registration of a single chemical is what you see here: physical, chemical, and fate properties, ecotoxicological properties in experiments, toxicological properties and experimental data, exposure assessments, emission scenarios, all leading to the industry. All of these data are packaged inside the registration dossier, leading to the industry making a judgment about risk, what kind of risk, how to mediate that risk, etc. And of course, it is anticipated, it's been seen many times already, that when the industry gets to that point and they say this compound exhibits significant risk, they almost assuredly know that it will not make it through the entire process. But in any case, it's very, very important. Also, then, these data are put into a database at ECHA in Helsinki called Euclid. And Euclid is linked in then to IPChem to provide, let's call it, global integrated information on concentrations of chemicals in the environment and everything related you need to for risk assessment.
2 minutes.
Okay. And I'll go to just this one and I'll stop. My colleagues at Vrije Universiteit Brussels are working on some interesting aspects. You, of course, are very familiar, much more than I am, about all of the molecular scale and bioassays, cellular bioassays that you need to measure the kinds of chemicals and their impact in water systems. Of course, we know a lot about how to collect these chemicals in the modern way, all sorts of passive sampling devices, etc. My colleagues have recognized that there are, of course, 100, 1,000, whatever number of chemicals exist in rivers, particularly in Europe. And what you are really interested, of course, is not necessarily having all the concentration data, but rather having the what is the impact of those concentrations on the organisms within the system. And my colleagues are working very interestingly about developing new tools to model the transport and behavior of chemical activity in water, not individual chemicals, but rather activity. And you can imagine from what you know that this is a tremendous challenge, and it's the early part, but it's, I think they will have a lot of fun doing that, and it'll be very important. Anyway, I will stop there. Thank you for your attention.